Right. So what we are going now to discuss is what we name the multiperiod problems. So what are the multiperiod problems? Is problems that for which the conditions are varying with time. But there are two different types of variation. The first one is the one that I'm going to discuss now, is that the processing conditions are going to change from one state to another one for a certain time. Okay, it's like if you operate during the summer and during the winter. I will then afterwards introduce another dimension, which is the time variation during a day, in which I'm going to create then relationships between what is happening at 1 o'clock and what is going to happen in the next hour. Okay, so let's first start with multiperiod problems. That means that we do not, in multiperiod problem, we do not consider the storage. We consider that the system can be operated in optimal conditions in each period. And each period is defined by a condition during the period and a duration. So it's during a certain time. The other time, which is will be treated later on, is when you have links between periods, which means that then you will have to look at the storage capacities, because what you do now is in prevision of the future, or it has at least a link with the future. Okay, so let us solve the first part. The first part is still concerning industrial processes, so it's mainly for the people that are doing in a post, for example, because the idea is to see, okay, let us consider that we have an industrial system, and this industrial system here has well, several boilers, a steam cycle here, and then several processes on the same site. And for each of those processes, you are able to draw a specific requirement, which can be then what you can see here. For example, it's an exothermic process. This is also an exothermic. This is an endothermic process. This is an exothermic one. So we have to take in the fact that we have processes that have to be heated or that have to be cooled down. And of course, you can combine the processes so that you will see the benefit of the integration. But then you will ask yourself, okay, for the nominal conditions, I can see a synergy. But what is happening if this one is not operated, or if this one is operated only when this one is available? Okay, so now I have a problem because I have to some extent to look at the probability that the two processes are made available in are operated together or not. Okay, and this is going to create problems, and the problems are to some extent shown here, because what you can see is that there is a big benefit in operating together. So this is the integrated site, and this is the if all the processes are considered to be separated one from the other. Now, if I'm doing the integration, the 22 megawatts are transformed into 9 megawatts. So if I'm combining all the processes, I have a big benefit. Okay, so I have 60% less energy consumption in the system. And here I can even see that I will have the need for a heat pump. Something which is also important is that the heat pump is needed for the whole system, but it's not needed for the system alone. So it means that if I'm looking at the process alone, there is no need for installing a heat pump. But in the integrated system, then it makes sense to have this heat pump installed. So which is also quite interesting. So it means that the temperature level here, which is available here, can be used by something else than the streams that could be involved in the heat pump. Okay, so it means that we have to be able to look at the whole system, and what you can see is that 30 additional % can be recovered by the heat pump in this case. So it's very significant. I'm starting from 60. If I'm starting from 100, I can profit from the integration by 40%, and then out the 40%, an additional 30%, so it makes 10 at the level of the whole system, can in addition be saved by the heat pump. So it's very important to understand this. However, what is also important is to understand how the systems the different processes do operate. And these are the profiles of the operation of the 5 processes that I have. And you can see that they are operated in very different modes during the year. Okay? So it means that I will not always profit from the whole, from all the benefits. And here is, in fact, the difference between the heat integration by considering that all the processes are operated under the nominal conditions. And the green part here is if they are operated in the average, by considering the average operation. Okay, and you can see that the shade is different. Here, I do not have any interest in installing a heat pump there, while if I'm in the red one, I have a big interest in doing it. So it's very important to understand what is happening during the operation. In addition to this, when I will decide to buy or not a gas turbine or a steam cycle, I have to realize that sometimes the processes are on or not, which means that I have to decide what is the best size of the technology that has to be added in the system. The same for the heat pump and for the gas turbines, for example. So the way we are going to do it is that, of course, we can analyze the composite curves and identify if there is an opportunity in adding a gas turbine, for example, or not. But we have to have a way to calculate the integration. And for example, here, these are the 3 different gas turbines that I have found in my catalog of gas turbines that are a priori good candidates. Now I have to choose which one is the best, considering the variations that could occur in the process. So what I'm going to do now is that I'm going to try to understand how to make the calculations of what is the best choice. So the first thing that I'm going to do is that I'm not going to model the whole year, because it would mean I don't know which is the size. Is it the hour? Is it the day? Is it the quarter of hour? Is it the monthly values? Okay, but I have to define how to divide the time into time slots. And I would like, and I know that the more I have time slots, the more the complex the problem will be. So I would be interested to identify a limited number of time slots that are representative of the operation of the combination of processes. Knowing that, I'm going to represent a typical year, which is not necessarily what is going to happen in the future. And the gas turbine, I will buy it for 20 years. Okay, so I have to do a statistical analysis that allows me to define a set of combination of productions, which means a set of level of production of the process JI in a given period. This is what I name. So it's a set of combination of solution or of operations. And for each of this period, I would like to know how much time I will be in this situation. So when I'm saying a time is the hour per years, but I could have also said it's the probability of being in this combination of levels of processes, of processing. Okay? So what I'm going to do is that I'm going to try to identify how I can represent the red line by a limited set, and the number of sets was, in our case, 10, which are combinations of levels of the different processes. Okay? And what we have done is the following: is that we have on the one hand the real level of the different processes. We have on the other hand the estimated level, so the blue line, and we would like to minimize the difference between the expected level in blue and the real level in red. By considering a limited number of periods, and the period is the combination of levels here. And I'm going to make the integral of these errors, and I'm going to try to identify what is the level of each of the process in each of the periods that will satisfy the represent the observed here. And one of the solution is shown here, so you can see that we have the blue line is not really fitting the red one. Okay, but the advantage is that I have a limited number of sets. So instead of having 8,700 hours, which could be the combinations, here I have only 10 different sets that are considered. Okay, and what we can see, this is the result of the calculation. So you have the number of hours during which you can see the set 1, the set 2, the set 3, the set 4. And for each of those one, then we have calculated the minimum energy requirement in terms of heating, in terms of cooling, and in terms of refrigeration. So what you can see is that it's sometime you are endothermic, it means that you have to supply heat to the system, and sometimes you are exothermic, so you deliver heat to the system. And here you have the frequency, and you can see that these are the three main operations here, which are representing most of the total time of operation. Okay, and now what I'm going to do is that I'm going to write for each period. I'm going to write the list of equations. So I have for each of the period, I'm going to write the heat cascade, including the utility flows. And what I'm going to add to this system is the calculation of the size of each of the units, which is in common between the different periods. Okay, so I'm going to calculate what is the level, at which level each of the unit is going to be operated, and by these constraints, I'm going to calculate what was the maximum size of the unit, and I will link this size to the corresponding investment. Okay, so if I'm looking at in another way, so I will over the whole year calculate the sum over the time slots, where I will have here the probability of occurrence of this time slot multiplied by the operating cost during this time slot plus the investment, and Y and S being the shared dimensions. On the one hand, it's the size of the technology and the existence of the technology. Okay? And by doing this, I will then write for each of the periods, I'm going to write the heat cascade and all the associated equations. Same for the inequality constraints. And I will calculate what is the maximum value for the x, which allows me to have the s, and for the existence. Okay? So the only element that are shared between periods are the size and the existence of the investment. What does it mean? It means that when I'm writing, I'm going to write really these equations, except that now these equations will be written for each of the periods. Okay? And then afterwards, I will make the sum over the periods and over the utility in the different periods. This one being related to the maximum value and to the existence of the investment. So it means that here, this constraint is saying that if I need the gas turbine only in one period, I will have to buy it. Okay? So the model is still linear, so it means that we have to do a linearization to be able to use it. But it's a mixed integer linear programming, which means that it is sometimes robust and efficient. And something which is also perhaps not necessarily really rigorous is the fact that I'm using the heat and updating the heat cascade with the same delta T minimum, which means that I do not take into account the fact that if the time during which I'm operating the unit is low, perhaps I would have reduced so the time is short, so it means that I have not a lot of time to recover the heat recovery investment. So normally I should have a bigger delta T minimum. Here in this case, I have considered that all the delta T minimum were the same. Okay. But nevertheless, so if I'm applying this into my problem, then I will have the final solution in which I will choose the gas turbine that is the best one, and I will have the objective function. Something which is important here is that perhaps I have bought a gas turbine which is not operated in all the periods. So, for example, I'm taking one of the solution here, and what you can see, for example, is that in there are periods during which, for example, the condensation turbine is not used, which makes sense. So these are the situations where it's better to directly use the heat coming out of the steam turbine rather than using a condensing turbine. But here you can see finally what are the situations, and nevertheless, due to the fact that you have some exothermic operations, it makes sense to go towards the use of the condensing level. Okay. The same for no, the gas turbine is always used, so it's mainly the heat pumping that is changing from one period to another one. So, for example, here you do not use the heat pumps, while here you are using it. So it means that we have now included into the design the operating strategy. So I have decided what is the size of the heat pump, and I have decided to buy the heat pump, although for some of the periods the heat pump is not used. Okay? And what I must say as well is that so here you have the heat pump, and you have also the fuel usage, which means that the backup boiler is more or less used depending on the choices of the other technologies. Okay? When you have an integrated system, it's really important to keep this in mind, because you have to have the equipment that allows to do the extreme conditions at the same time as you have to have equipment that makes you the best benefit. And in this case, so the system has selected one type of gas turbine, which is a small one, in fact, compared to the one that were proposed in the beginning. So if I'm going back to the list of gas turbines that were a priori proposed. Here, you can see that the one that has been selected is not the biggest one, it's the smaller one. Okay? Which is the one that has the best configuration.
And also, we use it for partitioning during certain periods. We need to install different ones because the adaptability is too small.
Yeah. So it's on one hand, it's possible that you will have to buy two instead of one, or you have to take to consider that you have a backup unit somewhere for making the peaks. Okay. So what is important here is that you have effectively an operating strategy for your system, and I must say as well that in this case, the decisions can be influenced by the market prices. Okay, because the only thing that was in this study, something that was varying was the level of operation of the different processes. But at the same time, you could also consider the price of electricity that is perhaps cheaper in the summer than in the winter. Okay, and in this case, you would have perhaps decided to operate in another way. So this is just to show you that this is as a function of the electricity price, what you will do in terms of the system operation. And you can see that you would have, so there are three situations. This is the maximum post-combustion. This is the gas turbine operation, and this is a low post-combustion. And what you can see is that according to the price of the electricity, you can have different operating strategy from the max combustion to the low combustion, post-combustion to the gas turbine shutdown. And this depends, of course, on the price of electricity you get. Okay, and this is perhaps also a drawback of using a linear programming problem. That if there is an interest for doing something, it does it at maximum possible. Okay, so it means that if the electricity price is low, is high, the system will perhaps see that it makes sense to just operate the gas turbine, even if I do not have to, if I do not need heat. And in the case of the linear programming, it will go to the maximum. That's it. There will be nothing that will limit this operation. Okay? Questions, Modis?